Hello, Kirtana, can you hear me?
Yes, sir.
All right, so which topic? What we did in the last class? Could you remember the topic we discussed? Just share it. Uh, yeah, Kirtana, do you have any doubt in the previous topics we have done so far? Uh, The field now. Yes, now I'm not getting a response from you, and please let me know if I'm audible or not.
Yes.
Okay, great. Now, so today I'll be explaining you about Lorentz forces. Okay, just let me uh, clarify the last time. Am I audible or not? Lorentz
Like,
force. Okay, so have you studied Lorentz force earlier? Kirtna, I'm
no,
asking, can you? No, right? Okay. So basically, whatever we have heard so far, that if there's a charge, okay. Yes, so we started from electrostatic. I said charge, if rest, provides magnetic field. If I start moving this charge, it gives you current. Okay. And when we are talking about the magnetism chapter, we said if charge is moving, okay, it will provide some magnetic field around the position and so on due to the electric field also, right? Basically, if okay, so motion of the charge can also provide you electric field. But there's one thing, more thing we studied that if there's a charge moving inside a magnetic field, then force will also be on that, right? So how we can interpret this? For this, I'll just make one graph, very simple. It's not a graphical thing. I just wanted to show you. Assume that this is one 2D plane I'm going to make, basically three-dimensional plane. Call this as so this is X plane, this is Y coordinate, and this is your Z coordinate. Okay. What my says there's a electric field in this direction. Okay, along with Y, along with Z, and then we have yes, there's a magnetic field also that is above, and there's a charge which is moving. Okay, so what is interpretation of Lorentz force? So basically Lorentz force is basically the total force exerted on a charged particle when this charged particle is moving, because if magnetic field is there, okay, if charged particle is on rest, so effect will be only due to the electric field. So what is Lorentz force? Total force exerted on charged particle when is moving in magnetic and electric field. Okay, look, when only electric field is there, you can say electric force. When only magnetic force field is there, you can call it as magnetic force. But when the combination of both presence, in that case you can call it as a Lorentz force. Is that clear? Kirna, is that
yes,
clear? Okay,
yes.
makes sense. Now we can actually think of one more thing. If I ask you what is the formula right now, so it depends upon the direction where it is moving. Okay, so right now I just give you two situations that magnetic field is this way, this way. So I will just try to calculate, let's say, three conditions. The first condition is if your charge velocity, okay, if velocity is in x component, it means charge is moving this way. So can you tell me, Kirtana, what will be the direction of magnetic force on this charge when velocity is in this direction? Just think of it.
Outwards,
Which direction?
outwards.
Outwards. Okay, makes sense. So it is outwards. So I can say, yeah, this is thing, right? So I can say the what is magnetic force? I can write it as Fm, which is equals to yes, which is equals to Q V cross B, right? So I'll just put the magnitude there because the angle between them is 90 degrees. QVB. And what is the direction? Outward in this case, outward is Z direction. Okay? Because you are doing I cross J, which results you K direction. That's the thing. So this, if I have to give this into the direction, so the whole thing comes out is, sorry, put that is in the magnitude because now magnitude we can keep because direction we know directly. That is K direction. Okay. Mean to say this. What about magnetic field? Basically electric field. So F E is nothing but Q times of electric field. And what is electric field? That is Q E times of K itself, right? So in this case, your F net comes out as Fm plus Fe is equals to QE plus QVB times of K. Alright. Also, if you further want to rewrite the same thing is E uh, plus QVB, sorry, Q is already we have taken up as common. So this is B times of clear. Kirtana, can you hear me?
Yes, sir.
Okay, yeah. So what I'm trying to say is P, yes. So this is how we calculate. Now, Kirtana, look at the case that can we have a case there? So what should be the case that the charge went out undistracted, okay, without any distraction? Mean to say, look, if electric field is there and charge is moving, so that's very simple. That electric field will provide force downside, so it will move in this way. Magnetic field is there, it will also provide some force in some direction, so it is getting distracted. I want a relation in which it went undistracted. So for that case, what you can say is, F net is nothing but result of one thing. What is that? Um, Q times of E plus Q times of V cross V, right? Is that clear, Krishna? Because I am saying it is going to be undistracted. In that case, net force is zero. Let's keep it zero. When in presence of E and P, charge moves undeflected or without effect of the fields. What does this mean? That the net force comes out zero. In that case, you can say because this is just a magnitude, you can actually go and say that Q equals to negative times of Q V cross V. Okay. Okay. So in that case, electric field must be equals to negative times of V cross V. Okay, what does this mean? Let me see carefully. The problem is very carefully saying that electric field should be this. The direction of electric field is like this. The result of this should be this. It means the force on the charge should be opposite, because that's only the possible, right? Because electric field always provide force in the downside. So force due to the Fm should be this way. In that case, if the magnitude comes equal, then you can also say this comes out equal. This is one case. Is that clear?
Yes.
Uh, it's clear, right? Okay, this is fine for now. Also, Kirtana, look, my network is actually not that good. Are you getting my voice clearly, or it's like lagging in between?
Please.
It's clear, right? Then we can move further. All right. So, okay, let's talk about case. Kirtana, did I discuss about the helical path in the last class? Like,
No.
look, if we were discussing if the charge is moving in a magnetic field, right? When I said if it is going this, if it is entering over here, it will complete a circle or something, right? We were discussing those kind of cases. So did I discuss about the helical path it is going to cover? Then we calculate omega and all. Do we had a discussion around that thing?
No.
Mm, okay, if not, so I think I can just start with that part. Okay, so look, if you know that if there's a charge, okay, now what I'm trying to say is, just look at that carefully. Electron is moving in this direction. Okay, so last thing with this is this, but no, that should not be the case. One velocity must be in this direction, this direction. One is in this way, one is in this way, so one must be this, and the magnetic is in this way, right? What is this? This way, this way, this way, this way, this comes in this way. But charge is this. Yes, it has one component of the cylinder component. This is one component, and this is one. Okay, so let's look for a case where the thing is looking like this. Maybe I think what happened. Just are you trying to unload this? Okay, Kirtan, there's a magnetic field inside inside the field. Then what over here is there's a charge which is moving this direction. So actually not in this direction because it does not make good sense to me. Ideally, let's remove it. Assume there is a magnetic field. This kind of plane is there. Okay? 2D axis I'm trying to make. Okay, this 2D axis. And there's a magnetic field in this direction. Yes, magnetic field is in this direction. So you have a
Sir,
charge.
the screen is blank.
You have a charge. The screen is black, right? Uh, okay, that's actually better than Yes, so in which sense I can go? Kirtana, can you see the screen now? Right.
Yes, sir.
I'll just I'll start the board again. Maybe you can see it in that case. Okay, so basically, if you see over here, I'll just paste the previous thing. Yeah, but yeah, Kirtana. So look, what I was saying that time is movement of charge when moving at angle theta with magnetic field. Okay, with magnetic field. So let's look at this how it works. I said this is magnetic field. Okay, and you have a charge which is trying to move at some angle theta. Okay, so we have to figure out what kind of motion it is going to follow. So Kirtana, if you see carefully, what will happen is you can just distribute this velocity into two ways. Okay, resolve this velocity into two components. I'm just making over here. So one component will go along with it, and one component will go perpendicular to it. If you say this angle is basically theta, sorry, if you say this angle is theta, in that case, you can simply, this is velocity, right? So you say this is v times of cos of theta, and this goes as v times of sine theta. All right, makes sense. Now, if you see Kirtana, this velocity and this two velocities are there. So let's look at this. What is the force due to this velocity? What is the force due to this velocity component? So F is equals to V cross B times of whatever the charge particle has, that is Q. So this V component is actually have a same angle, so this will F parallel, okay? Parallel mean to say this, it will be 0. F perpendicular will be nothing but F times, sorry, it will be Q times of B times of sine theta. And theta here is because you can see 90-degree directly, so that becomes QVB. Okay. No, sorry, actually there's a difference over here. QV sine theta is the velocity itself, so you have to keep it as a. So that's the formula right now. Now, what actually happens? What kind of motion it is going to follow? Due to the involvement of two different velocity components, v times of cos theta. Assume the particle was here right now. Okay. What it does, it will be applying a force. I'll just try to make it into 2D plane. Maybe you can see. Okay, so this is basically I just wanted to retain so that it will is just a second. Okay, this is one 2D. You can, all right, it's like okay. Yeah, something like this. It now style network issues steps little bit. Okay, look, I won't go for much of visualization. I'll simply put one helical shape over here. Charge angle. Let me see that. Yes, got it. I think it now you can see this image on directly put an image. So Krishna, what's happening here is there's a charge moving. Okay, it was moving in this X, Y. This is Y direction. This is so particle it was trying to so you can just this part, this parallel part, we discussed that V parallel is F perpendicular has a value what do QVD. We know the reason and theta actually. As angle theta, please theta becomes sine theta. This becomes 3 times of cos theta. So what happens is covering a helical path. If I ask you now what is the distance it has covered this? So this is nothing. If you see carefully, it started from this position, turned up the whole around, right? So I can simply say whatever the time it took to complete. Yes, I think it's fine. I'll switch off the different method. I'll paste that down. Yes. I'm going to figure out something. Kirtana, can you hear me?
Yes.
Okay, fine. So this is the last thing we have to discuss with this session. Yeah. Okay. So Kirtana, look, this is at angle theta. Okay. So I already told you this is V of sine theta. This is V of cos theta. Now, Kirtana, it's all about you how you actually visualize. So look, when this particle was here, due to force, okay, assume due to this factor, it was covering a complete circle. But also it has a particle. Look, it was supposed to cover this kind of circle, but because it has front side of velocity, so the particle which was supposed from here to here, it went instead this way, little bit this way. So the particle which is supposed to be just here, just up, it went up this way. So this whole length led it to complete a circle. Look, ideally it should be closing, but due to a velocity in the front direction, instead of closing, it went into like a helical path. Okay, something like this. So if I ask you, there's a lot of things we can actually figure out, okay, with this data. So generally, this distance between two helical paths, basically this is a helical circle, this is another helical circle. What's the gap between? This is called as pitch. So if I ask you what is the pitch, you can simply say, sir, because I can see, I know the velocity in this range. What is that velocity? This v cos theta. So pitch is nothing but v cos theta multiplied by the time. What is the time? If you see, the particle started from here, maybe here. It is covering the whole circle. Mean to say, to to make this gap of the distance, it has to cover the whole circle, right? If it is covering whole circle, this is nothing but v times of cos times theta times of time period. Okay, this is time period. Oh, makes sense. Now, if I ask you, Kirtana, do we know, like, if a particle, you can see this motion, this circular motion, as a, like, particle has a velocity this way. You can simply see particle has velocity this way. Uh, Object is moving this way. So particle has velocity this way. Object, someone looking from this side. You will see this situation, this kind of thing is there. In this case, particle always move a circle. We know the configuration of that circle. What is the radius of that circle? That is, uh, what is the radius of that circle? That is QB by NB, right? If you could remember that thing.
NB,
Is it this correct or incorrect? It's quite incorrect, right? It
NB
should be,
by kg.
yeah, exactly. It should be MV by QB. Look, that is the formula. But here, what is my velocity? That is V times of sine theta. Look, so that relation which we have used is very helpful over here, right? So here you can say the radius which it is going to cover is mv times of sine theta divided by q times of theta. Makes sense. What was the time period over here? The time period was basically 2 pi by omega. And you can say, sir, omega is nothing but whatever the velocity it had, whatever the radius it covered will be r. What is the r? That is 2 pi. Sorry, I can actually rewrite it over here. 2 pi by v sine theta times of r. And what is r? 2 pi r. R is nothing but radius, right? So, sorry, what we are doing over here. Yeah, that's fine, that's fine. First, let's complete the formula over here. In general, the formula comes up as r v. So, this 2 pi m v by vba. So, you can say this cancelled out. What we are left with only this thing. 2 pi m by v. This is the formula, right? Is it the formula or something else? Yes, there's a q also at the bottom. Okay. So this is the formula. And now if I ask you, this is the thing, what is the pitch? Pitch is basically distance traveled by charge between two uh, two revolutions. Okay? Basically, one revolution started from here, then another. No, actually, distance traveled by charge in one revolution. Okay, in one revolution. So yes, and also it should be, if you keep it horizontal, it will be much better in one direction basically. Because if you ask me what is the actual distance is traveled, so distance is each part, right? The whole circular length of another. But this is not the distance. We are just talking about this pitch, okay, between two successive that of things. So what is that? Velocity in that multiplied by time period. What is the time period? 2 pi m times of v cos theta divided by q. Kirtana, is that clear?
Yes,
Clear, right? Any doubt at this topic?
yes.
No doubt, right? Okay. So I will just look at something. Just a second, please. Yes, Kirtana. So I think we can solve some problem. Hmm. Kirtana, I'm just curious to give you one problem that there's a charge. Okay, look, see carefully the problem. There's an infinite long wire. Okay, having current I. There's a charge which is moving towards it from this point, head velocity u. Calculate the okay, makes sense. Calculate the minimum distance between them. Maybe yeah, you have to calculate the minimum separation between them. Separation possible. Okay. Initially, the initial situation is given as this. The distance between this and this is x naught. Kirna, did you understand the problem once? Please let me know.
Yes.
Okay, what's the problem? Can you explain it once? What's the main problem? Like, what's the problem in this?
Like
What we have?
particle moving due distance towards the current I with infinite long,
Yes.
and
Okay,
we
so
need to
why?
find
Yeah,
minimum.
fine, that's fine. Why do you think this problem is special? Like, what's the crux of this problem? Could you figure that out?
Like charges.
If a charge is moving, makes sense. Then just think of it. Uh, is it really? Is it easy problem? What do you think? It's an easy problem or what? You know what? We know that due to an infinite long charge, there's magnetic field. Right? How the magnetic field goes? It is always perpendicular. Right? Perpendicular. It means in this region, if you talk about the magnetic field is something like this. Okay, wait. What we can see that magnetic field is there, the charge is moving. Did you got some hint, Kirtana? Kirtana, have you got a bit of more hint regarding the problem?
Yes.
Why? Look now, I just explained once. Did you understand about the part like magnetic field inside in this region? The electric magnetic wire is there, current is going right. Due to this, if you look at this region, magnetic field here is this way. If you look at this side, it will be outside, coming out. Okay, these kind of magnetic fields are going to be there. In this magnetic field, there's a charge which is moving in this. So what the problem is, your magnetic field B, what's the formula for the magnetic field? Mu naught by 4 pi I times of, right, dl cross the distance, right, divided by the distance cube. If you rewrite the thing further on, 2 pi times, sorry, oh, yes, 2 pi times of what dl we are talking about. Where related to the dl part is 2 pi r divided by 4 pi r square was the r cancel. This is the thing, cancel, cancel. So the formula was 2 mu naught I by 2r, right? This is the formula. If you see here, the main part is your magnetic field is inversely proportional to this thing, right? It means if if you are at this point or if you are at this point, magnetic field here is half of the magnetic field here, right? Because it is inversely proportional to r. Okay, here if you say the r is this, Here it is 2 times of it. It means in this case the magnetic field is not constant. By the time you are moving towards the charge, towards the magnetic field, more force is applied. So what kind of situation is there? You can just think of it one thing, the charge is here, magnetic field right now at this situation is this way inside. What is the direction of force, Kirtana? Downside, okay. So downside is the force. So what, where you move finally? You move it somewhere here. You reach here. Magnetic field here is much more. Direction is this way. Force again, sorry. Yeah, velocity is this way right now, perpendicular this way. What is the direction of force? This side, right? But the problem is this force Fm is increasing every time. Why it is increasing every time? Because the reason is magnetic field is increasing when you are moving closer to it. Look, earlier what happened is in normal cases you had a uniform circle, but in this case you won't be having a uniform circle. It will be like this. Okay? It will be converging very fast. Understood, no point? Have you got this thing? Like
Yes,
what actually the problem wanted to say? Okay. So can you take this? Do you want to take it as a homework to solve this part?
yes,
Because
sir.
it's a good problem. Okay. All right. So this is I'm giving you as a homework. You should try to solve it, and I will. If you look, I will ask in the class next class. If you are not able to do, I'll explain this problem. Okay, complete problem. Clear?
Yes, sir.
Okay. I'll look for one more problem if I can get. No, no, this already we did. I think I can keep something from Lorentz force. Okay, this is problem one. You can take it as homework. I'm giving you one more problem. Question. In this question, you can take it. What I can take. So look, there's a two axis. This what happens is at this y-axis there's an electric field in this direction. Look, please look at this towards x direction. Okay, this is x. There's a particle which is entering inside this field, electric field with a velocity v. What's the coordinate of this point? 0, a. Okay, this is a. And sorry, I can actually entering. This particle is entering inside. Coordinate is 0, a. Okay. In this region, the whole region, there's a magnetic field coming outside. Okay, understood? So, because look, you can see magnetic field is in this way. Okay, force is coming towards me, so there will be magnetic field outside, right? Every time. So what happens is, it moved this way and came to this point, but something like this. Okay? Something like this. So when it came out of it, it directly came at 90 degree. Okay, with the velocity 2 times of v. What's the coordinate? 2a times of 0. Find e. And about the charge, mass, and charge, I think Q, and rest of the thing is given. Okay, so on the basis of this, you have to decide magnetic field is given in K direction. Okay, this is K direction. So you need to calculate magnetic field, electric field. Okay, clear, Kirtana? Understood this problem? Like what the problem wanted to say?
Yes.
So these two problem I'm giving you as a homework. Please try to solve it. If you're not able to make it, I'll give the solution in the next class. Okay. So Kirtana, that's all for the today's session. If you have any doubt before ending the session in this solution or something, if you want, please let me
No, no.
know. Doubt that. So yeah, that's all for the today's session, Kirtana. Goodbye. I'll share this PDF. You'll get the problems. Okay.